gets rid of dead space at the beginning here. So, infrared spectroscopy. Oh, why is it not? There we go. Now it's working. So typically we represent molecules with very rigid representations, but they're actually very flexible. They can wobble, they can rotate, and they can do this over a range of time frames. So for big complicated molecules like proteins, there's lots of ways they can flex and bend and such. And understanding how proteins fold and bend and flex is very important for understanding, how they function biologically. So motions can include things like rotations, translations, changes in bond length, bond angles, dihedral angles, ring flips, and methyl bond rotations. A whole bunch of different ways that molecules can move. So infrared spectroscopy is one of the primary ways that we study this. So IR radiation has a frequency range from about 10 to the minus 12 to 10 to the 12 to 10 to the 15 hertz. It's not negative frequency, it's high frequency. The wavelength is from about a micrometer, 10 to the minus 6, up to about a millimeter, 10 to the minus 3. So the wave number is from about 10 to 10,000 inverse centimeters. The longest waves have a wave number of 10. The shortest waves have a wave number of around 10,000. I mean, it goes a little bit below micrometer because technically the cutoff is the edge of visible light. But usually what we're looking at in an infrared spectrometer is a decent way away from visible. But yeah. So I guess the line is probably at wavelength of something like the bottom end is at 700 odd nanometers. So just a tiny bit, but this is sort of the whole spectrum. There's the visible range here. Here's infrared, what we're talking about. It bleeds into the edges of microwave and radio at the low end, and it's below red, so it stops at red light at the bottom of the visible. Now, wave number is in inverse centimeters. So if you take the wavelength, convert it to centimeters and 1 over that, the wave number of 10 to the minus 6 meter EM radiation is 10,000 inverse centimeters. 10 to the 4 inverse centimeters. The wave number of 10 to the minus 3 EM radiation is 10 inverse centimeters. And this is just useful to know because pretty much every plot of an infrared spectrum is in these units. It's in wave number. It's the standard way that infrared data is presented. Now, infrared transitions are all vibrational transitions. Because they are vibrational, they can be approximated with a simple harmonic oscillator, generally. And so that they have something, their energy levels are n plus 1/2 times some base frequency times h bar. But the space, that means the spacing between the energy levels is even. And it's that base frequency. So infrared IR spectroscopy, it's based on IR absorption by molecules that undergo vibrational and rotational transition. The vibrational transitions are more or less harmonic oscillators. So the transitions are basically evenly spaced. The potential energy resembles a classic harmonic oscillator. the fit is best at low energy levels, but generally you aren't dealing with high value energy levels. You're only usually doing 1 or 2. And IR radiation is in the range from around 1,280, no, sorry, 12,800 to 10 to the minus 1 centimeters, or from 0.78 micrometers to 1,000 micrometers in wavelength. Rotational transitions have small energy differences. They're at the low end, below 100, less than or equal to 100 inverse centimeters, with wavelengths greater than 100 micrometers. The vibrational transitions occur at higher energies. So if we want to look at rotational transitions, they would be off over here, off the end of this plot. This is a typical IR spectrum for a organic molecule. It is going from high wave number down to low wave number. This is benzene. So this is the CH bond here. This is the CH bond here. Basically, those CH bonds here. This is the double bonds from the aromatic ring are over here. Those vibrations. So these various peaks, this is transmittance, so the peaks are dipping down, correspond to various motions of the bonds, so you can actually get some idea about the structure, what kind of bonds exist by looking at where the peaks are. And then down in the low end, you have these sort of hard to identify peaks that are very fingerprinted. It's hard to theoretically predict where they'll be. You could run simulations and stuff, but they vary a lot for small changes in molecules, so they're good for identification. So there's a wide range of electromagnetic radiation. The energy of any electromagnetic radiation is H times frequency, or HC times wave number. So you could, your energy, what that means is that different energies allow monitoring different types of interaction with matter. So given that harmonic oscillator thing, the important thing that you get the transitions, so say delta from 0 to 1, that's going to be some V naught times H. Delta from 0 to 2 would just be twice V naught times H. And so, if this had a wave number of, I don't know, 900 inverse centimeters, this would have a wave number of 1,800 inverse centimeters. It's double. And from 0 to 3 would be 3 times. Because this is 1.5 minus half, this is 2.5 minus half, this is 3.5 minus half. And this would have a wave number of 2,700 inverse centimeters. So you might see all 3 peaks. The different energies allow for monitoring different types of interactions with matter. So typical IR spectrum for an organic molecule. So these are some examples. This is hexane, this is hexene, this is hexine. You get many more bands than UV visible, fluorescence or phosphorescence. The bands are also much sharper. The pattern is very distinct for a given molecule, except for optical isomers, which happen to be things where the patterns are identical. This makes it a very good qualitative tool. It can be used very well for compound identification. That's what we're going to do for our first lab. We're going to use IR to identify a variety of compounds. Kind of just a bunch of random stuff. It can also be used as a qualitative tool because the intensity of the bands is related to the amount of compound present. And with FTIR, you can get clear enough peaks and enough resolution that it works okay as a quantitative tool. It's not the best, but it is okay. And the spectra are usually shown as percent transmittance instead of absorbance versus wave number instead of wavelength for convenience. This is just the usual way they get presented. You can also quickly convert them to absorbance and see the actual peaks, which is useful if you're trying to do quantitative values. Qualitatively, we tend to use percent transmittance. So the theory of IR absorption is that we're dealing with molecular vibrations. So we can represent some masses as a harmonic oscillator. We can approximate them as if they were basically a mass on a spring. The vibrations of a bond as a mass on a spring. This works for wobbling, stretching, all the sorts of motions you can have. This is an approximate representation of atomic stretching. It works well for the lower energy levels. At the higher energy levels, the stuff tends to distort a little. It's effectively two masses attached by a spring. So if you had a spring with a couple of balls on each side, and you think about how it would wobble. So for a mass on a spring, force is equal to minus k times displacement from equilibrium. The mass times acceleration is minus k times displacement from equilibrium. Here they're showing it with a vertical spring, so y. So mass times the second derivative of y is minus ky. So y ends up being amplitude times sine omega t, omega being the angular frequency, and omega ends up being the square root of k over n. And the energy stored in that is 1/2 k times the displacement squared, as you see here. And then when you take this force and energy setup and apply quantum mechanics to it, you end up with the vibrational frequency. All right, well, first of all, if you just work out what the vibrational frequency would be for a couple of masses, your frequency, oops. This is frequency is just 1/2 pi to go from rotational to frequency, square root of k over mu, where mu is mass 1 times mass 2 over mass 1 plus mass 2. Yes. This is what's known as the reduced mass. And it's just the two masses multiplied together divided by the sum of them. So if you know the frequency and the atoms in the bond, you can derive K, the strength of that bond, as a spring. Single bonds tend to have Ks from around 3 × 10⁻², to 8 × 10⁻² newtons per meter. The average is around 5 times 10 to the 2. And double and triple bonds are 2 and 3 times as stiff. Because there's a double bond. And that vibration is because the frequency is proportional to the square root of k. Single bonds will have the lowest wavelength, then double, then the lowest frequency, then double, then triple. So the lowest wave number will be single, then double, then triple. So it's possible to calculate this for a pair of atoms. I may assign it as homework because there's some problems in the book of it, but I'm not going to put it on the test because it's just long. So the vibrational frequency is 1/2 mu. And for a quantum harmonic oscillator, the energy levels end up being this V, the vibrational quantum number, which is just an integer from 0. It's just a number, 1, 2, 3, 4, 5, 0, 1, 2, 3, 4, 5, and so on. Plus 1/2 times h over 2 pi square root of k over mu. And that is just v plus 1/2 times h times the vibrational frequency. So this Vm. And because of that, delta E, the change in energy, is going to be delta V, the difference in V times h over 2 pi square root of k over mu, or it's delta V, whatever that changes, that's just some integer times h Vm. And then if we want to find the frequency that you're going to oscillate at, the frequency you oscillate at is delta V times Vm. And usually delta V is just 1. You're really usually only dealing with transitions from 0 to 1. And then the wave number is 1/2 pi c square root of k over. But because the energy levels are evenly spaced, that let me change these to match the book because they use M, the natural vibrational frequency, and that gives you the energies. So the wavelengths are either the natural frequency of the vibration or a whole number multiple of it. Those are the frequencies of the light, which sort of makes sense if you think about it. So the harmonic oscillation model is good at low energy levels, like V0, V1, V2, but it's not good at high energy levels due to atomic repulsion and attraction. So as atoms approach, the Coulombic, the repulsion force adds to the bond force, making energy increase greater than harmonic, and then as separate, they approach dissociation energy, and the harmonic function rises quicker. So it's good for low numbers, not so great for high energy. But because of A in harmonics at low delta E, the delta V plus or minus 2, plus or minus 3 are observed, which causes the appearance of overtone lines at like 2 or 3 times the fundamental frequency. Normally delta V is plus or minus 1. So you will see usually plus or minus 1 for delta V, but sometimes you'll see 2 and 3 because of these anomalies. Now, there's a few different ways that bonds can bend or stretch. So we can start with bond stretching. Bond stretching can be symmetric. So you have both sides going out from the middle and going in to the middle. That's symmetric. Or you can have asymmetric, where one side goes in, the other side goes out. I'll have some animations. I should have some animations on the next slide. And you can also have bending. You could have in-plane rocking, where they're both bend in the same direction, in-plane scissoring. So, and then you can have in-plane scissoring, and then you can have out-of-plane wagging, where they're both moving in the same direction, and then out-of-plane twisting, where they're moving in and out, where one moves into the board and one moves out of the board, cut out of the board. And here are some animations. So here's symmetric stretching. Here's asymmetric stretching. So symmetric stretching, you get the idea being that, the middle doesn't move, the outside moves in and out. Asymmetric, you sort of, the middle moves where the outside moves back and forth, kind of. There's scissoring in plane. There's out of plane twisting. You can see it's twisting around. There's wagging. And here's rocking. Here's another illustration of them with CH4. Here's the symmetrical stretch. They're all moving out or in. The asymmetrical stretch, some of them are moving out, some of them are moving in. Yes, you have a question in the chat. How do you tell the difference between out of plane and in plane rocking? So you have some defined plane that's your reference. So here, sort of the plane is perpendicular to this backbone. That's why you have in-plane rocking. While twisting, you can see it twists relative to the backbone. That's how you differentiate. A lot of the times there isn't really any difference. You can get motions that are functionally identical to each other. We're going to talk about CO2. For CO2, there's two motions. One is in plane, one is out of plane, and they're basically the same thing because it's symmetrical. Here's a symmetric bend. Here's an asymmetric bend. Here's an asymmetric stretch. Here's a symmetric stretch. If it's hard to tell the difference, they probably have the same resonance frequency anyways, so they end up degenerate. So telling the difference isn't that big of a deal. Now, the number of vibrational modes that a molecule will have, there's actually a fairly straightforward formula for it that depends on the number of atoms in the molecule. So the number of vibrational modes for nonlinear molecules, the number of types of vibrations is 3n minus 6. For linear molecules, the number of, so this is non-linear linear, where n is the number of atoms. For linear, it's 3n minus 1. And this is why there's so many peaks in IR spectrum, because there's so many vibrational modes. But the observed vibration can be less than predicted for a few different reasons. One, you can have symmetry. You can have a vibration that doesn't actually change the dipole moment. If the dipole moment doesn't change, then you don't get any electric charge effectively moving. You don't generate any light. So the dipole moment has to change. So, oh, I think this. This isn't working because the battery died. Quickly do something about that. Or at least it's acting like the battery died. Okay. So one way that things can be less than predicted is because of the symmetry. So for example, in CO2, this mode of the two outer oxygens moving back and forth symmetrically around the carbon doesn't show a peak because the dipole doesn't change. Because the molecule remains, symmetrically balanced. So it could be symmetric and there's no change in dipole. You can also have situations where the energies of two vibrations are the same. The vibrations could be functionally identical. And then you might have situations where the absorption intensity is too low, so they just don't show up very easily, or the frequency in question is beyond the range of your instrument.
So how do you know
This is a linear molecule, like CO2. A nonlinear molecule would be something like H2O, where it's dead. It literally isn't in a line.
That's what I was thinking, because when you're before.
Yeah, it's in a line. It's just a symmetry thing.
Oh.
That gives you an extra. Being lined up perfectly in line gives you a chance for sort of an extra oscillation. So, for example, any diatomic molecule is linear. So HCl has one mode. CO2 has four modes, 3 times 3 minus 5. But H2O would only have 3 modes. But for CO2, not all these modes. So CO2 has 4 modes. You would expect to actually only see 2 peaks. Because this mode is not active. The dipole doesn't change as the CO2 symmetrically moves in and out like that. Because the distribution of charge still remains, balanced in the middle. This mode is active, and then these 2 modes down here are essentially just the same thing rotated 90 degrees. So they have the same frequency. So they're degenerate. So we'll see here are some animations. So in order for a molecule to absorb IR radiation, it needs to have a vibration at the same frequency as in light, but also it needs to have a change in its net dipole movement as a result of the vibration. So the net dipole moment here remains 0. Doesn't change. There's no dipole here. And it stays 0 the whole time. So that's IR inactive. These 3 modes are IR active, but these 2 modes are functionally identical because it's bending up and down or bending forward and back. They're basically the same thing. So to have the same energy, you only get 1 peak. So CO2 you would expect to have 2 peaks. So here is an example where we can calculate the absorption frequency for the CH stretch with a force constant K of 5 times 10 to the 2 Newton meters. So let's first calculate the mass of our hydrogen and the mass of our carbon. So mass of the hydrogen, 1 times 10 to the minus 3 kilograms per mole of hydrogen, divided by 6.02 times 10 to the 23 atoms of hydrogen per mole of hydrogen, gives us a mass of a hydrogen of 1.66 times 10 to the minus 27 kilograms. For carbon, it's 12 times 10 to the minus 3 kilograms per mole, so it's 12 times as much as the hydrogen. It's 1.99 times 10 to the minus 26 kilograms per atom of carbon.
Why is it the 6.04?
That's Avogadro's number. It's the number of
Oh, yeah.
particles in a mole. Yeah, that's our conversion from grams to count. So this is sort of the general conversion. The atomic mass in grams. We're trying to get this in kilograms, but basically anything. If you look at the atomic mass of something on periodic table, if it's 1, which is what the 1 here is, be 1.66 times 10 to the minus 27 kilograms. I think hydrogen is actually a little bit higher, but I think we're assuming we're working with an actual just bare proton instead of, because the number on the periodic table is sort of the average among all the isotopes. There is a little bit of difference, but it's beyond the resolution shown here. And then so the reduced mass is going to be multiplied together, divided by their sum. So 1.66 times 10 to the 27 times 1.99 times 10 to the 26 divided by 1.66 times 10 to the 27 plus 1.99 times 10 to the 26, which is going to be basically 12 over 13 times 1.66 times 10 to the minus 27, which comes out to 1.53 times 10 to the minus 27. And if we substitute that into our equation for wave number here, 1 over 2 pi c times square root of k over mu. 1 over 2 pi c is 5.3 times 10 to the minus 12 second inverse centimeters. K is given as 5 times 10 to the 2 newtons per meter, divided by 1.53 times 10 to the minus 27 kilograms. We take the square root. This comes out as 3 times 10 to the 3 inverse centimeters, or 3,000 inverse centimeters. So the wave number will be 3,000 inverse centimeters. So you'd see a peak at 3,000. And if you look at the charts, the massive charts of all the peaks that exist, we'll find that CH bonds are between 2,850 to 3,300. And because the environment around that bond is going to change the springiness of the bond, that makes sense that it varies around there, but it's around 3,000. Because different CH bonds in different environments have different values. Again, there's that enormous table in your book. Here's a smaller version of that table. Here we can see CH bonds in alkanes are from 2,850 to 2,970. In alkynes, the CH bond, this is a bend, not a stretch. But the stretch is, you can see 3,010 to 3,095. In alkanes, that CH bond is 3,300. And then these are bending modes as well. So the alkanes have 2 modes, the alkynes have 2 modes. Aromatic rings, there's another range of them, again, around 3,000. So this is sort of a rough table with a bunch of these different bonds, which you can use for most of your identification. That giant table is just a more detailed one showing like all the possibilities. And they didn't retypeset it, they just reproduced it. So, qualitative analysis and compound identification is more or less the main application of IR. We use infrared with NMR and mass spec, and that in the late 1950s more or less revolutionized organic chemistry because it decreased the time to confirm compound identification 10 to 1,000-fold. They cut identification times down by enormous factors, several orders of magnitude. And the general scheme is you examine what functional groups are present by looking at each group frequency region. So here in this range is single bond stretch. So CH stretch, OH-NH stretch. Then here are the triple bonds, the double bonds. And this is the fingerprint region, the skeletal vibrations of bending and rocking in here. Single bond bending, single bond rocking. These are single bonds bending and rocking and skeletal stuff. So you can examine different frequencies. So structural stuff you get down to about here-ish because it's hard to get actual information out of this fingerprint region because small, it's not so predictable. But if you know, if you want to identify that you have a compound you've previously measured, that region is very useful. So lots of functional groups will occur in certain regions. The approximate frequency of many functional groups, CO, CC, CH, OH, can be calculated from atomic mass and force constants. So you could do that sort of calculation to get the rough range where you'd expect them, or you could look them up on the table. And the position changes a little with neighboring atoms, but it's often in the same general region, and it serves as a good initial guide to identify compounds, but it's not positive proof. So this is wave number. These are the various, these are stretch, OH, NH, CH, CO, double bonds and triple bond stretches, some double bond stretches. Here's some CC, CO, CN backbone stretches, and then bends for The bending vibrations are also down in this region. As well. So basically, the things with hydrogen, because they're effectively lighter, have higher wave numbers, higher frequencies. Heavier stuff, lower frequencies. Single bonds down here, then double and triple. And so here sort of, this is rock, this is bend, this is double bond stretch, triple bond stretch, single bond stretch with hydrogen. So here's some more, examples of bonds and regions. It's sort of redundant because I grabbed this from a different book. And here's a big table that's pretty easy to read of this stuff. Different compounds and their different strengths and the intensity. So some of these are strong, while some of these are less strong and broad or medium. I'm not going to go through them all, but you can sort of see how, things with hydrogens are higher rate frequencies, and then double bonds, triple bonds are a little lower, and then the single carbon, nitrogen, carbon, oxygen, carbon, carbon stuff is lower still. And again, another good solid table. I think I just showed this earlier. So it's just a repeat. I just wanted to get all the tables up in slides so you can reference them. So the fingerprint region from around 1200 to 700 inverse centimeters is the region of most single bond signals. A lot of them have similar frequencies, so they affect each other and give pattern characteristics of the overall skeletal structure of a compound. And the exact interpretation of this region of spectra is seldom possible because of complexity, but complexity leads to uniqueness, which makes it really useful for identification of organic compounds. So if you want to check it, do I have this thing? Or what is this thing that I found? Like forensic stuff. Is this cocaine, this strange white powder, or is it sugar? Or if I'm doing food science, what sugar is this sugar that I just pulled out of some substance? Because there's a bunch of very similar sugars out there. So here are the various, here's a couple different spectra. And here are some individual these are both CO bonds with other things around. But you can see we both have that C double bond O, which has a nice clear peak, which is the C double bond O here. And these are a little bit different because this is CH3 CO CH3, well, this is CH3 CO2 CH3. And yeah, the way you identify things is with computer searches. So most modern instruments have reference IR spectra on file. You could have as much as 100,000. You could easily have 100,000 compounds. I honestly don't know how many compounds we have in our database. We have a database. Actually, we have like several databases. And it's not that hard to add more. So you could get another database and add it if you get it in the right format. And so you can do matches based on the location of the strongest band, second strongest band, etc., and give you an idea about the overall skeletal structure of a compound. A lot of these will give you an estimation of how well the fit is, how accurate, give you a percentage of match kind of thing. At least ours does. An exact interpretation is seldom possible because of complexity, but that complexity gives you uniqueness, which means, the search can be quite effective. So for example, the Bio-Rad Search IT database has something like 200,000 IO spectra. Again, I literally don't know. I'd have to dig through the files to try and get an idea, but it's a lot. And that's like the stuff we got with the instrument. I mean, it had some holes, which I've added to fix for later labs. Now, it's not as good as UV visible for quantitative analysis. Because the spectra is more complicated and because of the narrower bands, you're more likely to deviate from Beer's law. IR instruments often have lower light throughput and weaker detectors, and there is often high background IR. That's less of an issue with an FTIR instrument. The FTIR helps deal with both of those problems. It's difficult to match reference and sample cells. That's a real issue. And changes in epsilon, A equals epsilon BC, are relatively common. But a potential advantage is good selectivity, since many compounds have different IR spectra. And one common application is determination of air contaminants. So you can run air through an IR thing and check how much, carbon monoxide, methyl ketone, methyl alcohol, ethylene oxide, chloroform, etc., are in that sample. I can use like a flow through shelf cell to that if you're using FTIR to get it fast. So you can get a continuous readout kind of thing. I think we have a gas flow through cell for one of the instruments. I've never used it. So here's an example of a spectrum for a substance with the empirical formula of C3H5N. We want to figure out what the compound is. Well, we have a CH peak around 3000. So we definitely have CH in it. And that peak corresponds to the alkyne number, I believe. No, that's. So yeah, this CH peak is sitting, a bit below 3000. And this peak here corresponds to a C with a triple bond to the end. So now we have a C triple bond end and 5 hydrogens. This gives you this is basically the only possible structure. So you can build the structure from the knowledge that there's a C triple bond M, and you have a bunch of CH bonds. I think I just asked you to identify what. I'll give you some peak numbers and ask you to identify what it would correspond to. Just look at the chart kind of thing. I'm not going to make you build structures like that. No. So this is a nitrile or alkyne group. It's like peak identification, and then you can work it out. But I don't want to make you do that. I don't want to grade it either. Yeah. Yeah. This isn't ortho. That has no aromatics, and then there's allelopathic hydrogens, and so you can put together this structure. And there's one or more alkane groups from that. Here's another thing, so you can see that this has a CH stretch, a CH bend, a C chlorine stretch, and you put together sort of this structure vaguely. I'm not going to go into the details because I'm hopeless at it, so I don't want to grade you. So okay, we can do a little bit more. So let's talk a little bit about instrumentation. Traditional IR instrument is similar to UV visible. Light source running through a sample and a reference chopper, feed it into a sensor. The main differences are the light source and the detector. The light source is infrared, the detector detects infrared. The light source has to produce IR radiation, one infrared. And you can't use glass because glass absorbs infrared radiation. If you look at a glass pane with an IR camera, it's just black. And there are several possible types of light source you can use. One of these is a Nernst glower, rare earth metal oxides, zirconium, cerium, or therium that heat electrically. You apply current to a cylinder, it has a resistance to current flow. It gets hot between about 1200 to 2200 degrees Celsius. This causes light production. It's basically black body radiation. And you can use a Nernst glower between about 670 to 10,000 inverse centimeters. You need good current control or it overheats and gets damaged. But, like, good current control is not that hard to do. Lots of things need good current control. It's a solved problem. A glow bar is similar to a Nernst glower, but it uses a silicon carbide rod instead of a rare earth oxide, and it has a similar usable range. It's a hot rod, both of these. It's basically a light bulb, but in the infrared. You can use an incandescent wire source, which is a hot wire. So this is often a tightly wound nichrome or rhodium wire that's electrically heated. This is basically you ever seen an electric space heater? This is electric space. One of those ones with the coil wire, that's electric space. It's a toaster. It's the same principle as an Nernst glower or a glow bar. It's a lower intensity than an Nernst glow bar, but a longer lifetime. Nichrome wire is used as heating wire in things like toasters and lots of other things. And electric furnaces and other kinds of stuff. You can use a CO2 laser. CO2 laser gas mixture is 70% helium, 15% carbon dioxide, and 15% nitrogen. And a voltage is placed across the gas, exciting the nitrogen to the lowest vibrational levels that populate the asymmetric vibrational states of the CO2 through collisions. And the infrared output of the laser is the result of transitions between the rotational states of the CO2 molecule and the first asymmetric vibrational mode to rotational states of both the first symmetric mode, stretch mode, and the second bending mode. You don't need to remember this. It gives off a band of around 100 inverse centimeters at a range from around 900 to 1100 inverse centimeters. It's a small range, but you can choose which band is used, and many compounds have IR absorbance in this region. And it's much more intense than certain black body sources. So it's useful for if you're trying to detect something specific that you know the range you're going to measure in. It's not so useful for sort of general analysis. It's also what you use in a laser cutter to cut a lot of stuff, because it turns out lots of things absorb in that range of wavelengths. So the good laser cutters use CO2 lasers so they can cut transparent materials, like plastics. And then some others. You can use a mercury arc for the far IR with wavelength that's greater than 50 micrometers. You can use a tungsten lamp for the near IR. That's from about 4,000 to 1,000 12,800 inverse centimeters. Now, there's two main types of detectors in IR instruments. There are thermal detectors, which basically measure temperature. Because the IR gets absorbed, heats something up, you measure a change in temperature. So a thermocouple is two pieces of dissimilar metal fused together at the ends. When heated, the metals heat at different rates. This creates a potential difference between the two metals that varies with their difference in temperature, creates a voltage that you can literally measure directly. These are usually made with a blackened surface to improve heat absorption. And you put them in an evacuated tube with a window that's transparent to IR. So not glass or quartz. The IR hits and heats one of the two wires. And you can use several thermocouples to increase sensitivity. Thermocouples are used as thermometers all the time. Most electronic thermometers, your probes, are thermocouples. It's one of the simplest way to do an electronic thermometer. It's pretty reliable. It's fast responding. The other ways you can use like a thermistor or other things, but those need more power. The thermocouples are very common. They also can be quite small, which is good for like a probe thermometer. A bolometer is a strip of metal, platinum or nickel, or a semiconductor that has a large change in resistance to current with temperature. So this is like a thermistor. A thermistor is a resistor that changes its resistance with temperature. And as light is absorbed by the blackened surface, the resistance increases and the current decreases. These are very sensitive. And then there are photoconducting detectors, where a thin film of semiconductor on a non-conductive glass surface sealed in a vacuum. The absorption of light by the semiconductor moves from non-conducting to conducting state, decrease in resistance, increase in current. And this has a range of around 1,000 to 333 inverse centimeters at room temperature. That's more like, a more electronic way of detecting. So there's thermal, and then there's photoconducting. And then there are pyroelectric detectors, which is something like a ceramic lithium tantalite material that gets polarized. There's a separation of positive and negative charges in the presence of an electric field, and that polarization is temperature dependent. So this is another thermal detector. And it measures the degree of polarization related to the temperature of the crystal. It has a fast response, and so it's good for FTIR. I really should look up what we have in our instrument. I don't actually know. Now there are other components. You need a sample cell that needs to be made of some sort of IR transparent material. You can use NaCl plates or potassium bromide pellets. You have some windows, gaskets, spacer, sample goes in the middle. So we have a few sample holders like this. This is a classic transmission sample holder. We're not going to do any potassium bromide pellets. That's where you mix a powdered substance with potassium bromide powder and compact it into a little pellet. You shine the IR through because potassium bromide's transparent to IR. But we do have a liquid sample holder like this, which I'll show you guys on Thursday. So it's not what we're gonna mostly use. Monochromator or reflective grating is common. You can't use a glass prism because that absorbs infrared. So you end up using a grating instead. That uses interference. And then this is sort of the traditional overall instrument design, where you have a reference and a sample and a chopper. Combined, you need a chopper to discriminate source light from background to IR radiation. And you put the monochromator after the sample cell. So this is not done in UV visible. You put the monochromator before the sample cell because letting too much light in might damage what you're looking at as photodecay condition. But IR is at such lower energy that you're unlikely to do this. And this also allows the monochromator to screen out more background infrared light. The source is weak, you need long scans, the detector response is slow, so you get rounded peaks. That's for a traditional, instrument, which is, nobody uses those anymore. Everyone uses FTIR these days. So Fourier transform IR is an alternative. It's based on a Michelson interferometer. Here's the basic idea. Again, the interferometer here effectively, the light from the source is split by a central mirror into two beams of equal intensity. The beams go into two other mirrors, they're reflected by the central mirror, recombine and pass through the sample to the detector. So the sample is after this, but this is the monochromator effectively. This is what's choosing the frequencies. There are two side mirrors, one is fixed and the other is movable. As you move the second mirror, the frequencies that interfere positively and negatively change based on the lengths. The light and the two paths travel different distances before they recombine. You get constructive and destructive interference. And as the mirror is moved, you get a change in signal. So as you move the mirror through time, your signal on your output, your sensor will vary, and that will correspond to different wavelengths. And then you can use a Fourier transform to transform that. So you get destructive interference when two waves from the same source travel different paths to get to a point. And this can cause a difference in the phase between the two waves. And if the paths differ by an integer multiple of a wavelength, they'll be in phase, they'll add up positively. You'll get that. But if they differ by an odd multiple of half a wave, then they'll be 180 degrees out of phase and cancel out. And so what you get for any one wavelength, as you move the mirror, you get a sine wave that corresponds to that wavelength. So if you have multiple wavelengths, like this, you get multiple sine waves that add up together. And so you can take this, displacement over centimeters, which is really a time thing because you're measuring it as you move the mirror back and forth. And then you can do a Fourier transform to convert it from this intensity versus distance or time to intensity versus frequency. You can extract the frequency data with the Fourier transform. And the trick to this is that a technique for doing very fast and efficient Fourier transforms was figured out. It's called the fast Fourier transform, or FFT. You'll see that all over the place in computing stuff because it's incredibly useful. Because Fourier transforms are really useful, but doing them strictly formally is a giant pain in the butt normally. But the fast Fourier transform is sort of a way to use some tricks to very quickly do a Fourier transform by basically splitting things in half repeatedly. And so it's an algorithm, it's a really useful algorithm. And the resolution, delta V is 1 over the distance traveled by the mirror, basically. So the resolution in wave number, because these are in wave number in inverse centimeters, but it's 1 over the distance traveled by the mirror. The longer the mirror travels, the better the resolution. So, I have to dig up this video, but I've seen some stuff for like really top of the line. Some of the guys sort of putting back together an old, but one of the best Fourier transform spectrometers out there that can even do UV visible Fourier transform stuff because it's precise enough. And its mirror moves a long way. And it can evacuate the entire instrument. You can pump all the air out so the air doesn't interfere. And so some advantages of FDIR compared to normal IR, it's much faster, seconds versus minutes. You can use signal averaging to increase the signal to noise ratio, because every time the mirror moves back and forth, you get basically another measurement. Or, so you could do that whole bunch of measurements. Increase the number of scans to get better signal to noise ratio. And a higher inherent signal to noise ratio because there's no slits, there's less optical equipment, there's a higher light intensity. Basically, you're not throwing out any of your light in the way that you're choosing wavelengths. And so it has a high resolution that's like 0.1 inverse centimeters. The disadvantages, so it's single beam that requires collecting a blank. So you have to take a background and then take the sample. You can't use thermal detectors, they're just too slow. So you have to use very fast detectors. In normal IR, you scan through the frequency range. In FDIR, you collect all frequencies at once, basically. And I think that's a decent place to stop for today. We will be doing our first lab on Thursday. I think we'll just do the lab on Thursday. We won't have any lecture because we're well ahead on this. So we'll finish off IR stuff next week. Yeah, we'll just do a lab starting at 1. Because there's no reason not to just use the time. Some of these labs take a long time. No, I don't want. I want to make it more likely that we get to leave early.
How long will it last?
I'm not 100% sure, but probably will be done by, 2:30. We probably just take the lecture time in truth for this particular lab. It's not super long.
What is,
So we're going to be doing identification of various unknown substances using the IR machines. So I'll have a bunch of unknowns for you to identify. You'll run them and check them against the database, collect all the data. That's the idea. And the various sorts of materials from, just solid stuff to powders to liquids. That's the idea.
hey,
So I'll see you at 1. See you at 1 on Thursday. So I'm gonna end the meeting. I will post the recording up.
you know what our first exam is?
When we finish IR after that. So
Oh, okay.